Okay, so we'll be talking about areas again in this section. And first, let's just recall the difference between net and total area. When we talk about the net area of a function, we're taking the area of any region below the x-axis to correspond to a negative quantity, right? And so anything above the x-axis becomes positive. And so the net area is just the sum of these two quantities, right? So in this case, the net area of the shaded region is going to be a negative number. Whereas if we talk about total area, this is an absolute quantity where we consider everything to be simply a positive area, much like the area calculations you probably used to do in grade school. And so in this section, what we're concerned with is, how do we compute the total area when it's not just one curve and the x-axis, but now you have two curves forming a region, right? So in this example, we have y is equal to square root of x and y is equal to x cubed as the two curves. And what we're trying to compute is this region in between them. And it's not really that difficult, actually, if you try thinking about extending what we do for the area under a single curve and between the x-axis, right? Because this is pretty much the same thing. This is, say, the curve of f of x, and below you have the curve y equals 0, right? So it's kind of like you have two curves here. Now, how we can approach this is, consider first this whole region, right? So I'll call this the blue region, which is the area below the square root function, right? So this is this integral of square root of x dx from 0 to 1. And in order to get that area that we want to compute in between the two curves, well, why don't we just subtract this area, which is the integral from 0 to 1 of x cubed dx. Right? And that makes sense. Right? And when we subtract, we get exactly this area that we need in between the two curves. And I'm not going to evaluate these. You can just practice on your own. These are easy integrals. And really what this tells me is, in order to compute the area in between two curves, if you know the curve that's on top, right? So if you know that f of x is larger or equal to then g of x on the interval you're considering from a to b, then you can compute the area by simply computing the integral of the difference, right? So if you go back to the previous page, remember that from a property of integrals, this is also equal to the integral of the difference of two functions, square root of x and x cubed. Now, if you think about it from the perspective of, again, your Riemann sum definition of definite integrals, well, it also makes sense, right? If f of x is on top and g of x is below, and let's say that's a and that's b, remember that for Riemann sums, we divide this whole interval into many subintervals, right? So n subintervals in general, and take the limit as n goes to infinity of the total sum of all the areas of the rectangles we get. But in this case, in order to approximate this area, your rectangles don't look like this anymore, right? Where it's just bounded above by f of x and below by the x-axis. Instead, your area element is going to look like this, where you're using both information from f and g in order to tell you what the height of your function is, right? So for instance, if we take the left endpoint of your subinterval as your height, right, then the height here is going to be f of x I star, right? So using the left endpoint, it's f of a plus I minus 1 delta x minus g of a plus I minus 1 delta x. And so in general, you can simply consider this approximation in the limit to have, well, each rectangle is now going to have height f of xi star minus g of xi star. And you multiply it by delta x, the width of that rectangle. Add them all up, take the limit, and you get exactly this definite integral. All right, so the formula makes sense, both geometrically and in terms of our Riemann sum definition. Now, usually, when you're just given equations for your curves and you're not actually given what the graphs look like, you have to do that extra step of finding the points of intersection, right, among these curves in order to find out, you know, what's that x value you end your integral with? What's that x value you start your integral with, right? So what's your a and what's your b? So in this case, you have y equals square root of x minus 4, y equals square root of x over 2, and y equals 0. And what that's going to look like is, so let me draw our axes here. Y equals 0 is simply the x-axis, right? So that's not a problem. We know what that looks like. Y equals square root of x minus 4 is just a square root function, right? But with x minus 4 instead of x. What that means is it's translated 4 units to the right. And y equals square root of x over 2 means, well, it's just a square root function as well, right? But you're compressing it by a factor of 2. So it kind of looks like that. So now we're considering this region here, right? And we want to compute the total area of this region bounded by the 3 curves. Right, so it's this region here, which I'll border by blue. Okay. So first question, again, what are our points of intersection? Well, we know that 4, 0 is 1. Right, it's the intersection point of the first curve and the third curve. That was pretty simple. We know the origin is another. Right, it's the intersection point of root x over 2 and 0. And I mean, it's easy to show that you don't get any other intersection points, right? Just do the algebra. Solve for x such that y equals square root of x over 2 also gives you y equals 0, right? And 0 is the only solution there. That gives you the origin. But what about this point on top? The intersection of the 2 square root functions. Now again, just equate them. So let's do that here. Right, and well, we can square both sides and solve for x. Right, and so we get x equals 8 there. And when we plug 8 into our functions, we get square root of 8 minus 4, which is 2. Or square root of 8 over 2, which is also 2. Right, so which means this is the correct intersection point. But notice here now that there's a difference here between this region and the region that we started with a while ago, which again I'll show you. Here we just needed to compute the integrals from 0 to 1 of the curve on top, which gives us this region here, and the curve on the bottom, which gives us this region here. And so we subtract, and we get the region in between. In this case, it's not exactly that simple, because the square root of x minus 4, well, it's only actually defined when x is larger than or equal to 4. And so you notice here that in our formula on the previous page where we said if f is larger than or equal to g, then you take the integral of f minus g. Well, your f function here, the function on top, and your g function here, the function on the bottom, differ depending on what your x value is. Right? In fact, at x equals 4 is exactly when the bottom function changes. The top function is the same. It's still going to be this y equals square root of x minus 2 function. Right? So your f of x is still root x over 2 in both these intervals from 0 to 4 and from 4 to 8. But now look at the bottom function. From 0 to 4, it's just 0. From 4 to 8, it's now the square root of x minus 4. Right? And so this is something you have to consider when finding area. Right? It's always top minus bottom, which is what this f minus g formula tells you. Right? This gives you the height of each rectangle in your approximation. So you have to determine carefully what functions on top, what functions on the bottom, subtract them, and then take the integral. Therefore, the area here is going to be equal to, well, the area of this region from 0 to 4. Well, that's just the integral of root x over 2 dx, right? It's just your definite integral from our basic definitions. It's just the area under the curve and above the x-axis. But then we add the integral from 4 to 8 of now root x over 2, which is still your function on top. And let me just shade the region right here. But now the function on the bottom is the square root of x minus 4 dx. And now the area is the sum of these two integrals. Okay, so this is nice. Again, I won't evaluate the integral here anymore. I'll leave it to you to do for practice. But I'd like to end by now considering the same problem here, where, let me just draw all those curves again. You have y equals root x over 2. What did that look like? Yeah. Y equals root x minus 4. And y equals 0 as well. And what I claim here is that there is another way to compute the area of this region without having to split it up into two integrals, right? And the title of this slide sort of gives it away. It's seeing x as functions of y, or as a function of y. And what does that mean here? So remember, whenever you're asked to graph a function, it's usually, well, for instance, y equals x squared. How would you graph that? Well, you plug in x equals 2, and then you get y equals 4. And so you plot a point, and you do the same for each value of x to get all these points and connect the dots. Right? So x is called the independent variable, y is the dependent variable. But now what if we switch them? Right? What if we view these functions, right, as x equals a function of y instead? Well, and why are we doing this in the first place? Well, consider this. If we now consider these as functions where for every value of y, right, I'm getting a function not on top or on the bottom, but a function on the left and a function on the right, where that value of y gives me a specific x coordinate, g of y, and a specific x coordinate f of y to the right. Well, using the same idea as our Riemann sum, you can also actually form an area approximation here using n subintervals, but now instead of the height of the function giving you the height of the rectangle, now you're picking a delta y that tells you what the height of the rectangle is, and for each y, it's the width of this rectangle that varies. And we know exactly what that width is, right? For each subinterval in y, you just have to select a yi star, similar to selecting an xi star for your vertical rectangles, and form your Riemann sum like that. And, well, when you take limit as n goes to infinity, well, what does this mean? This is just the integral of f of y minus g of y from a to b, right? Where a and b basically denote where we start and where we end. Therefore, for this specific example, we can also actually compute this integral by computing, well, what is the lowest value of y here? It's 0. That's where we're starting. And what was this point again? It was the point 8, 2. So b equals 2. That's where we're ending. So imagine that for each value of y, you get a horizontal segment here. And the length of each horizontal segment depends on that specific y coordinate. And we know what these functions are. This function written as x equals a function of y is now, so it's y squared equals x minus 4, or y squared equals, or x equals y squared plus 4. And this one is y squared equals x over 2, or x equals 2y squared. So the function on the right is y squared plus 4. The function on the left is 2y squared. Take the integral from 0 to 2. And this should also give you the area of the region that we're looking at. And you should be able to check that this area is equal to this area over here.